So I'd like to start my talk. And this is the title of my talk. The Assimilation of GPM DPR Spectral Latent heating using the particle correlation, observation error, covariance in Kalman gain. My name is Yasutaka. It's a Microphysics Research Institute in Japan. So, this figure shows the GPM DPR latent heat product. So GPM DPR is a dual frequency precipitation radar on both GPM core satellite. This latent heating is retrieved from the DPR observation. So latent heating is a very important information for precipitation process. The latent heat can be used for the simulation to modify the temperature and hydrometers inside the precipitation system. So the data assimilation improves accuracy of the nowcast and short-time forecasting by improves the initial condition to assimilate the SLH. So I'd like to explain the data assimilation system used in this study. I will use the local forecast model called LFM, operated by the Japan Meteorological Agency. This purpose is nowcasting and the aviation weather forecast. The simulation method is a combination of 3D bar and 1 hour forecast cycle. The horizontal resolution of the simulation system is 5 km. The forecast model is a non-hydrostatic model. The horizontal resolution is 2 km and the forecast length is 10 hours. The frequency of the forecast is 24 times a day. The boundary condition is given by the mesoscale model called the MSM. MSM is the regional model of the JMA. The MSM is a non-hydrostatic model with the horizontal resolution of the 5 kilometers. The orange line shows the forecast area of the LFM. So this slide shows the flow diagrams of the data assimilation system. So first, we get the first guess from the MSM. So we repeat 3D bar and 1 hour forecast 3 times. And finally run 3D bar to create the initial condition of the forecast. This is cost function. This is cost function of 3D bar. The cost function is described by the background error and observation, background term and observation term and Babish terms. So we will use this system to assimilate the SLH. The simulation of latent heat will modify the tendency from the cloud microphysics scheme. However, the simulation must be keeping the balance between the dynamics and physics. The standard 3D bar does not keep the balance because it does not include the time integration in the constraint condition in the optimization. On other hand, the nudging method can modify the tendency during the time integration of non-linear mode. So we choose the nudging method. In this study, we use observation errors, includes the particle correlation in the nudging method. In the nudging method, the model state is gradually relaxed towards the observation. The amount of the corrections is given by the nudging term during the time integration. So we have used the nudging term that includes the Kalman gain. In many cases, the traditional nudging methods use the relaxation function and interpolation operator instead of the Kalman gain. The nudging term is added to the temperature tendency in the cloud microphysics process. The nudging coefficient is given as a function of time. The function is defined as the contribution increased around the observation time. The element process is cloud microphysics that are related latent heat shown here. The nudging term calculates the modification to the sum of these processes. And the next is the background error in the Kalman gain was estimated by the NMC method for the 1 hour intervals. So we estimate the B in the temperature coordinate. The temperature coordinate will be explained later. So the structure of the background error has been greatly simplified. The horizontal error correlation is ignored. However, the nudging coefficient as a time filter also works as a special filter due to the advection and diffusion of dynamics. The error correlation in the vertical direction is not ignored because the tendency errors are strongly correlated in the same phase of higher meteors. So we estimated the background error covariance in the vertical correlation only. Next, I'd like to consider the observation error. The space-borne radar observed precipitation system from space, so we can assume that there is error correlation in the vertical direction. The right panel shows the precipitation intensity and SLH of DPR. The SLH profiles are different for convective and stratification precipitation. So it's considered necessary to define the observation error according to the situation. So first, we classify the observation error covariance by the precipitation pattern of the SLH product. The SLH product are classified by 6 types of the precipitation patterns in the tropical region and 6 types of the precipitation pattern in the mid-latitude region. So latent heat is dependent on the temperature in the precipitation system. So statistics value of the observation error and background error are calculated on the temperature coordinate. If there is a temperature inversion layer in the atmosphere, such inversion layers are rejected in the statistics. This covariance is converted to the observed altitude coordinate and model altitude coordinates and used in the Kalman gain. This slide shows the covariance of the sum of observation error and background error for each precipitation type. You can see that the convective type has larger values in the lower levels. Other than these types could be used because the sample size was too small and the noise was too large. The inversion of the covariance is given by the Moor-Penrose inverse matrix. In advance, we store computed inverse matrix and create the lookup table. The lookup table is used in the nudging. However, this inverse matrix is not perfect and contains a small error. You can see that the error is slightly larger in the lower temperature. I believe that this is not a practical problem. So this slide shows the effect of the error correlation. In these figures, x-axis shows the latent heat and the y-axis is altitude. The dotted line shows the altitude at 0 degrees Celsius. The blue line is the inversion. The orange line is increment using the correlated R, and the green line is the increment using the diagonal R. If the background error is same as observation error, then the increment is half on the inversion. Using the correlated R, we got the result we expected. If we use the diagonal R, excess increment, so excess increment is computed. In normal setting, the result is shown on the right panel. When using diagonal R, its increment are large. So next we will show the situation dependency. The increment given are the same as in the previous slide. So we can see that the increment are different depending on the precipitation pattern. For example, the convective type, the positive and negative contrasts are lost. So this slide shows procedure for nudging. So first, we calculate the transformation matrix from the observation data and first guess. So next, we take the inverse matrix from the lookup table. The lookup table according to the precipitation pattern, and assign the inverse matrix to the Kalman gain. This Kalman gain is used during the time integration to correct the tendency. So I'd like to show the result of the data assimilation using actual observations. The experiment was conducted in the case of heavy rainfall, which has caused serious disaster in Japan. And the left panel shows the distribution of DPR SLH. So this movie shows the latent heat of the model. In the model, the black lines show the path of DPR. The changes are occurring before the observation arrives here, because it is filtered in the time direction by the nudging coefficient. The analysis increment is shown in the slide. This is the temperature increment and water vapor and hydrometeors. So you can see that not only the temperature, but also the water vapor and hydrometeors inside the precipitation systems. This increment, hydrometeors are modified in precipitation systems. In particular, rain and snow have changed significantly. The impact of nudging SLH on precipitation forecasts is shown in this slide. So you can see that in the test experiment using SLH, the precipitation area is wider than the control and closer to the observation. This is the 3 hours forecast. You can see that the forecast of the precipitation area is closer to observation. This slide, and in the 6-hour forecast, after the time, the distinct difference are lost in this case. So this is the result of the precipitation verification. It was verified using FSS. The left panel shows that FSS of difference between the control and test for each scale. So you can see that the score of the smaller scale has improved. The right panel shows FSS as the read times. Test is on improvement side, but not significant. This is summary. So latent heat nudging method with Kalman gain has been developing. The situation dependent observation error were introduced, and the appropriate treatment of observation error correlation was introduced. The diagonal observation error covariance in correct estimate the large correlations. And the result of the assimilation experiment, the fraction scale for precipitation was improved in the very short range precipitation forecast. So for future work, so we will increase the number of samples using ensemble forecasting to improve the accuracy of the observation error covariance. So thank you for your attention.
Thank you very much. We have a few questions. One question from Yufei Zhang. What is the dimensions of LUT? What is the dimension?
Temperature is discrete, 60 levels. So the locative is dimension is 60 times 60.
60 by 60.
Yes.
Okay, thank you. And I think that was clear. So the other question from Peter Yan, does the Kalman gain have correlations with, for example, humidity?
No. Only latent heat.
Only with latent heat?
Yes.
So there's no correlation with humidity?
Yes.
Okay. So that's it for, we had only 2 questions and you answered those questions. So thank you very much.
Thank you.
And we move on